Assalamu alaikum. Welcome to lecture 6 of data mining. So today we will continue with our discussion on data preprocessing. We had discussed data cleaning and data integration and had just started data reduction. So we'll continue with the techniques that fall under data reduction and then move on to data transformation and hopefully towards the end, we will start with data discretization. So that is the idea for today. We also have a quiz at the end of the day at 1:35 p.m. So the quiz is of the same format as last time, 10 minutes, and you have about 15 minutes time window to solve the quiz. So any questions from the previous lecture before I get started?
With two fingers unlocked. Device locked. 12:32 p.m. Voice call. Incoming WhatsApp voice call with Carmen. Out of pager.
Just give me a second. All right. All right. So any questions? Can you see my screen?
Yes, sir.
So we were talking about data reduction, which essentially means that we want to reduce the size of the data while keeping the data still relevant for our particular analysis. So in other words, we would like to remove redundancy or any other unrelevant information and keep the information that is relevant for our particular task. So within data, just give me a second. All right. Okay, so generally data reduction can be divided broadly into 2 to 3 categories. The first category you can say is attribute reduction or feature reduction. So this is the first category. And the second category you can say is numerosity reduction. And the third category, which is kind of rarely used in practice, you can call it in general compression, data compression. So the first one is feature reduction. So feature reduction, as the name suggests, is we want to reduce the number of features or attributes relevant that we actually use in our analysis. The original data set may have a large number of features or attributes. We would like to reduce them for our analysis. And the idea is that in the reduction, we want to reduce or remove those attributes that are redundant and do not contain any relevant information for our particular analysis. So within feature reduction, again, there are two general categories. One is called feature extraction, and the other is feature selection. So in feature extraction, generally and feature extraction is also sometimes used interchangeably with dimensionality reduction. So whenever you see dimensionality reduction, it usually is referring to feature extraction. So And we started talking about dimensionality reduction last time. So in dimensionality reduction, we are reducing the number of features, but first we transform the original features into a new feature set and reduce the features from the feature set that we have obtained after transformation, not in the original space, but in the transformed space. And there are actually a lot of techniques that fall under this category. Uh, we talked about last time PCA, so principal component analysis. So PCA basically transforms the original set of attributes into a new set of attributes such that the variance across or variance along the new attributes are high, or in other words, the attributes are arranged in such a way that the first attribute in the new space has the highest variance of the data, the second has the next highest, and the third has the next highest. And obviously, since the data is in terms of variance, you can then drop some of the attributes. Uh, the assumption is that the attributes with low variance have low information content and they can be dropped. So we talked about this last time briefly. Of course, some implementation might have slight differences. So let's say X is our data matrix and it's of size n by m. M is the number of dimensions or features, N is the number of observations, and this is our original data space. And let's say after applying or doing PCA on this data set, which of course would require some pre-processing like normalizations and finding the covariances, we won't go into that detail. You will get a matrix W, which is generally called a matrix of principal components or eigenvector matrix, and is of size m by m. M is, of course, as I said, the number of dimensions. And in this matrix W, each column or the columns are the eigenvectors or the components, principal components, and they are ranked. So the first column is the vector, eigenvector with the maximum eigenvalue, or the vector, if you project a data on that, it would have the maximum variance. And the second would have the next highest variance and so on. So given this uh, matrix W, you can create a new matrix W, let's say, let me call it W star, by keeping the first k uh, dimensions, and where of course k is less than m. And then you can use this to generate your new data set by simply projecting your original data set. This is matrix multiplication, x multiplying with w prime, and this will give you x prime, which is the new data matrix, and its size now is n into k. So PCA is applicable, quite popular. It applies only to primarily numeric data sets. It cannot be applied to categorical data sets. Uh, and it's used for dimensionality reduction. It's also sometimes used for visualization. How so? Let's say your original data set had, let's say, 20 attributes. Obviously, you cannot visualize 20 attributes on your computer. So you transform it into 2 attributes and then visualize the data set. And the assumption is that these 2 attributes are the ones that are most informative in terms of variance. So, and then you can study your data in just 2D as opposed to 20D. So, as I mentioned earlier, there are lots of techniques in this category, and for each technique, there's a lot of theory behind it. We cannot go into the theory of each of those, but it's still important to know at least the names of techniques that are out there and some brief idea of where it can be applied and where it cannot be applied. So I'm going to mention some other techniques. So I talked about PCA. Of course, PCA has many variants as well. So there is something called a kernel PCA, which can do nonlinear transformations as well based on the kernel that is used for transformation. So the original PCA is linear transformations. Okay. So, and then we also have what is known as ICA. It has a very similar name to PCA, which means independent component analysis. So in ICA, in PCA, we were finding a transformed space in which variance was high or variance was ranked. While in ICA, we are trying to find a transform space based on statistical independence, not variance, but independence. We would like to have dimensions that are independent from one dimension should be independent from the other and so on. So generally, this technique is applicable to time series data. And generally, it, it, it separates the time series data into several components. Each component is assumed to be independent of the others, or uh, you can say is the whole idea is that we want to find those components that are independent, statistically independent from the others. And then, of course, the whole time series signal is the sum of those independent signals. So, of course, as I said, it's applicable primarily or mostly to time series data. Uh, One application, for example, in time of sound blind source separation. So people who have from the EE background, who have more background in signal processing might have used ICA there. So blind source separation means that let's say there are 4 people speaking in a room, there's one signal coming in. This technique may be able to separate those 4 people's signals into separate signals, and each signal is assumed to be independent of the other because there are 4 people speaking. So this is ICA, primarily used for time series. It can be applied to others as well, but for other cases, I think PCA is more or less appropriate. So that's PCA, sorry, ICA. Then let me briefly mention what is known as multi-dimensional scaling, which is also sometimes abbreviated MDS. So multi-dimensional scaling is another feature extraction technique or dimensional reduction technique. In this case, we basically transform the original data space into a new space, of course, with reduced dimensions, such that distances between objects slash observations are maintained. So you notice that in the various techniques, there are different criterion that we are trying to satisfy. In PCA, we want to maximize variance. In ICA, we are trying to find statistically independent components. So in this case, we are trying to find a space such that if we project the original data into the new space, the distances are preserved. So this is the goal or the criterion that is used in multidimensional scaling. And so in this case, what is required is you need to have a similarity measure for quantifying similarity between data objects. So let's say if I give you 2 objects, x1 and x2, you should have some way of quantifying x1 and x2, similarity of x1 and x2. Let's say this is 0.3. So if you are able to do that, and you can apply, of course, you can do this for numeric data sets and other data sets, but you can also do this for nominal nominal, and let's say even ordinal. Nominal is actually more harder, but ordinal data sets. So you may not have an actual function for the nominal, but you might have a table that gives you the values of similarities between different objects. So for example, let's say we have a nominal data set with two attribute, color है एक attribute, and let's say दूसरा attribute हम ले लेते हैं uh, so color and let's say shape. ठीक है ना? Of course, shape has, let's say, 3 values, color, let's say, has 3 also values. So you can still use this as long as you have a way of quantifying the similarity. Let's say you have a color, let's say we are observation R, red color, and shape, let's say, is rectangle. And if you are able to find the similarity of this or quantify the similarity of green, let's say with rectangle, so if you are able to give some number to it, maybe even a human can give a number to it, then you can apply multidimensional scaling. Of course, you can apply to numeric data set as well, but for example, PCA was not applicable to numeric data set at all, but this can be applied to numeric data set as long as you can define a similarity value between any pair of observations. So multidimensional scaling so basically preserves or tries to preserve distances in a transform space. Okay? So that was another approach. Another approach is what is known as non-negative metric factorization. Non-negative matrix factorization. So in this case, so we have the data matrix X. This is our data matrix. One assumption that you have to make, and usually this is true for many applications, is that this is non-negative, meaning that there are no negative values in the matrix X. Okay? So if this is the case, then you can break this matrix down as two matrices, a matrix, let's say A and B. So original matrix was, of course, N into M. So N into M, so we can have N into K and then K into M, where of course, again, K is less than M. Otherwise, there is no point in having NMF applied. Okay? So this is a decomposition that we desire, and the goal is of the approximation. So X is the original, and let's say X asterisk is the approximated value obtained by multiplying with A and B. So what we would like is the difference between X and X star is as small as possible. So this is the criterion that is used to used in finding the matrices A and B in non-negative matrix factorization. So once you have found this, so you can use, for example, A. So how many A has basically N into K. So this is a reduced form of your data set. So you can use this for your analysis. N is the number of observations, K is the number of features or attributes, and this is the reduced form of your data set. So non-negative matrix factorization, again, is applicable only to numeric data set. It is, again, generally beneficial when you want, beneficially appropriate or more appropriate when you want to retain distances, just like multidimensional scaling. So it is good if you want to do clustering, and you may apply NNMF before to the data set. And that's pretty much it, I think. And of course, for okay, one final thing, and then I'll come back to that. And finally, In the neural network domain, you can use the autoencoder. So autoencoder has become very popular in recent years, and we will discuss autoencoder again later in this course. So I'm just debating whether I should discuss this now in somewhat more detail or maybe later on. I think probably later on. But just the big picture, autoencoder is what? So basically, it's a neural network, is a feed forward neural network. So it takes as input your data matrix X, or let's say one observation of that data matrix, one small X, and it also outputs the same X, but so it goes through, so it outputs the same X. So in other words, input is X. X, of course, is the matrix, all n examples. So usually in a neural network, you give those n examples one after the other. Okay, so I'm writing it like that. So it would have some hidden layers. And let's say the smallest hidden layer would have some output Y. And then those hidden layers would then increase back to the original size output layer, which is again of the same size as M. M is the number of features. So you're kind of reconstructing your input to back to you're reconstructing the input in the output. So this is again, but of course, this would be an approximation because it had gone through some smaller number of features. So you have to train this. You have to have a loss function. Usually, loss function is trying to minimize the error between X star and X. Once you have trained it, you have a trained network, and when you feed a new X into it, you'll get a Y. Y would be of a lower dimension. You can fix that. So let's say M input dimension was M. So you can have the hidden layer to have K dimensions where K is less than M. So for each observation, then you can have K features, which you can then use for future analysis. So we will discuss autoencoder in somewhat more detail when we discuss outlier analysis, because one of the more popular techniques nowadays for outlier analysis is using an autoencoder. So autoencoder meaning that the input and output are desired to be the same. So we can use the input to train or get the output. But once we have trained the network, we can use it to generate features that are obtained at the hidden layer. So autoencoders are quite powerful and have also become quite popular recently in the industry. Uh, they can be applied to numeric data set as well as to categorical data set. So for categorical data set, you can do some kind of encoding. And so for example, let's say you have a categorical attribute color, and color, let's say, has three possible values, R, G, and B. So instead of using symbols R, G, B, you can encode this color as a one hot vector, or we usually call it one hot vector of size 3. So in this case, in which only one value is 1. So 0, 0, and 1. So this combination of three values, 0, 0, 1, means that this observation is green. Similarly, if you have 1, 0, 0, this means that this is red. And similarly, 0, 1, and 0, this means that this is, sorry, the second. So this is basically green. The second one was blue, RGB. So you can convert categorical numbers or attributes to numeric values using one hot encoding, and then use those as input to the autoencoder. So you can mix, in other words, categorical attributes with numeric attributes, with ordinal attributes, and so on. So that's why this is also quite powerful. So in all of this discussion, we talked about K, and we wanted K to be less than M, because that's the whole idea of dimensionality reduction. So how do you find K? Of course, in all of those applications, in all of those examples or method, you have to fix K. But what is the best K? That's the question. So, so that best K usually is application dependent. So if you really want to find that in a more systematic way, we can usually use a wrapper approach. Wrapper approach essentially means that, let's say your eventual task is, let's say, clustering, and you have a evaluation measure for clustering. So what you do is you take different values of K. K is equal to 2, 3, 4, 5 until M. And for each values of those K, evaluate the performance of your task, let's say clustering, and you will choose that K, or you will retain that K that gives you the highest performance for your particular task. So usually it happens that, especially in dimensionality reduction, uh, as you increase number of Ks from 1 towards M, the performance increases, and then it peaks at some point, and then it starts decreasing. Why does it decrease? Because in all of these methods, uh, we are using sub criterion to find the best K. So after that number of Ks, and for many applications, performance starts to decrease. So you will then retain that K for future analysis. Of course, this has to be done in somewhat brute force way. You have to choose multiple Ks, run your algorithm, test, evaluate it, plot the graph, and then maybe decide what is the best K for your particular application. All right, so any questions? So this was a whirlwind tour of dimensionality reduction or feature extraction. So I've given you some techniques and some brief idea of their criterions and their applicability. Uh, you can always find more details by looking up relevant books and on the web. So details of these are also not given in your textbook. So, but you need to know some of these techniques as a data miner so that you can decide which one to use for any particular application or task. All right, so any questions? So the next category of attribute reduction is feature selection. So in feature extraction, we transformed the original M features into some new dimensional space and then selected the features. While in feature selection, we select in the original feature space. So let's say if you have M features, from these M, we want to select the best K, where of course K is less than M. Okay? So, so, so obviously, let's say, how many possibilities do you have? So, कौन से K आपने लेने हैं, ले सकते हैं आप? So let's say कोई simple सा example ले लेते हैं, A, B and C, ठीक है? 3 attributes हैं. So M is equal to 3. So what can you do? You can select A, right? You can select B, right? You can select C, right? You can select AB. You can select AC. You can select BC. And also probably you can select nothing. although that's trivial. So, so what is the number of possible options that you have here? So that is actually equivalent to the power set. So it's 2 raised to power of 3 is equal to 8. So, so if essentially for any given problem, we will need 2 to the power of m options, right? And usually m can be large, even if m is in dozens, 2 to the power of m is going to be a large number of options. But in many practical applications, m can easily go into the hundreds and even thousands. So the number of options for selection is tremendous. And obviously, we cannot search all of those options. We will have to use some brute force or greedy approach to select the best uh, set of attributes for our application. So in this case, also wrapper approach is commonly used. Uh, I would say, yeah, sometimes wrapper approach as well as uh, some internal or a, you can say deci deciding criterion. Wrapper approach is the criterion at the end of your final task, but you might have some other criterion that you can apply right away. So, so usually we use some brute force, greedy heuristic approach. Uh, so, so we have A, B, and C. So, so greedily, basically, we'll select the first best attribute. And how do we decide that first best attribute? This criterion that I mentioned earlier on. So that criterion is somewhat application dependent. So you cannot generalize it to all tasks. So, so one criterion could be, let's say, for example, let's say 10 attributes are A, B, and C, and then there's also a fourth attribute called class, and your task is classification. So one simple way of deciding which attribute to retain for this classification task is to find the correlation between each attribute and the class attribute. And A could be, let's say, numeric, A could be categorical, and class usually is always nominal, categorical. So numeric and categorical attributes के relationship ढूंढने के लिए you can use, for example, information gain, or you can also use entropy. So you can use a criteria of entropy to find which attribute is best for this classification problem. So let's say you had found entropy for A with respect to, of course, class. So keeping that with respect to class, okay? And you also found for B, and you also found it for C. So generally, lower entropy means that there is uh, greater dependence between that attribute and the other attribute. So since this is classification, so if there is greater dependence, we will keep that attribute as first. So let's say entropy of A, I don't know what those numbers are, 0.2, let's say kya dete hain. Entropy of B, let's say 0.3 hai. Entropy C ka, let's say aap kehte hain 0.4 hai. So you will first choose then A, and if you want to choose more than one, then you choose B. And of course, you won't probably choose C because that will mean taking all the attributes. Okay? So this is the general idea of attribute subset selection or attribute selection. And in this case, we are doing greedily selecting the best and the next best until we have reached the desired number k, which you can set a priori. And and also you can use a wrapper approach also, meaning that let's say your ultimate goal is clustering. You select a combination of attributes, do clustering and check what is performance, and then find which combination of attributes give you the best performance. So that is the general idea. Of course, you can reverse the order also. Generally, selection is the more commonly used order. You can also do, uh, you can say, removal. So let's say you start with all three attributes, and then you say, I remove the one that is the worst. So I remove C, and I'm left with A and B, and so on. And then let's say if you want to choose one, then you remove B, and you're left with A. So greedily increasing the number of attributes or greedily reducing the number of attributes, both of them are identical. They can be used with the same criterion like entropy, and also uh, you can, of course, put this in a wrapper approach as well. So in this case, of course, you're only trying m options. So it's a greedy approach as opposed to 2 raised to power of m options. Okay? So, which is of course linear in the number of dimensions. So any questions? All right, no questions. So we have talked about attribute reduction. Within that, we talked about feature extraction and feature selection. Okay? So now let's talk about numerosity reduction. So in general, numerosity reduction is reducing the number of examples. But sometimes uh, also reducing the number of values also. So I'll mention the difference. One technique is primarily about reducing the number of values. So not necessarily just dropping some features or attributes, but dropping some observations, or somehow combining those observations to reduce the number of observations, which in which case would mean uh, reducing the number of values. Okay. So in this case, again, there are many techniques, and we'll just quickly uh, do a survey. So the first one generally is called model-based, meaning that we are assuming that you have some model for your data, and then using that model, you are reducing the number of uh, observations or numbers of values in your data set. So again, at this one, I won't go into great detail. You can think of, for example, regression analysis. And generally, model-based approaches are not very popular in most uh, data mining. They're more popular in traditional statistics because the whole idea is that in model-based approach, you are assuming that you know something about the data. In most data mining applications, we don't know much about the data. So it's more popular in statistics and other domains that are heavily statistic dependent. So regression analysis could be one of them. Um, you have some regression model like linear regression model, your multilinear regression model, or even log linear regression model, or for example, in bioinformatics or biomedical, you sometimes have what is known as the odds ratio model. So things like that, if you have such models, then you can build such model on your data and then use that model to generate a smaller set of data. So that's the idea. So we won't go into more details beyond that. So what is more commonly used is what is known as a clustering-based approach, which again is in some ways model-based, but not parametric, it's non-parametric. So clustering is a non-parametric approach. You don't have, for example, in log linear model, you have a parametric model. So you have y is equal to, for example, some set of parameters w1 x1 plus w2 x2 and so on. While clustering doesn't have such kind of parameters. It has other parameters, but they are not those parameters that are common in parametric models. So in clustering models, the idea is that you cluster the data, you will have multiple clusters, and for each cluster, you choose some representative samples only. So if I maybe want to draw this, let's see. Let me hide this first. So in other words, let's say you cluster your data. Maybe you have found this big cluster here with various observations and maybe another cluster here with smaller observation. So instead of retaining all the observations within these two clusters, you retain some representative samples. For example, from the big cluster, you maybe retain some ones at the boundary and maybe one in the center. And for the smaller one, again, for some in the boundary and some in the center. The idea is that since you have clustered the data, you know some behaviors of the data, and you would like to retain that behavior with fewer number of examples. So you know some behavior, some pattern, and try to keep that pattern by taking only a few examples rather than all examples. So let's say there were 10,000 examples in your original data set. The top cluster had, let's say, 500 examples. The bottom cluster, let's say 10,000. Let's say the top cluster has 7,000 examples. The smaller cluster has 3,000 examples. So from the bigger cluster, 7,000, you might select, let's say, 1,000. And from the lower, you also select 500, and you're left with a data set of 1,500. So this approach can be used to reduce the set of data. Again, we are assuming that the data would cluster very nicely. If it doesn't cluster very nicely, then really you can't do anything. And we'll talk about clustering in more details later on. Let's say you are not able to find any grouping your data. So maybe all your data is uniformly spread. So if it is uniformly spread, obviously you can't do anything to reduce the size of the data. There's no pattern or no distribution in the data. So this is the general idea behind clustering-based numerosity reduction. Okay. So the next approach that we'll talk about is sampling. So sampling, basically, as the name suggests, is we are selecting uh, examples from a larger body of examples. So in statistics, we have what is known as a sample and we have what is known as a population. So population is the entire set of possible examples for your analysis. From that entire set of possible examples, we would like to select a sample which is representative of that population. So, and the techniques that are commonly used are the most popular, of course, is a simple random sampling or SRS. So simple random sampling can be done with replacement or without replacement. And let's briefly discuss that. First of all, random sampling. So let's say if you have 100 examples, right? So what you do is you generate a uniform random number between 1 and 100. Uniform random number between 1 and 100. Of course, if you're doing it using some programming language, this is just like one-liner. So whatever that number comes out, you select that example. Let's say you have indexed the examples from 1 to 100. So let's say you run the random number generator, you get, let's say 35, you select 35. Run it again, you get, let's say 66, you select 66. Run it again, let's say you get 2, and so on. So until the desired number of examples are extracted or retrieved from the data set. So this is simple random sampling. But there are two options here. One option is with replacement, and the other is without replacement. So meaning that let's say you have generated a number, let's say you got 35, then you got 36, and you got 2, and then maybe later on, maybe you got 35 again. Random number generator can give you 35 again, right? So if this was without replacement, so you cannot, so it means that you have already taken out 35, you cannot take out 35 again. So you will have to generate a new number and then select another example. But if it was with replacement, then of course, after selecting 35, we are assuming that 35 is placed back into the data set. And when 35 is generated again, you select it again. So with replacement may give you a data set with duplicates. So you need to be aware of this constraint, uh, especially if your algorithm uh, causes problems with duplicates. So with replacement will potentially give you duplicates. So without replacement, of course, would not give you duplicates. But there's a slight other theoretical difference between the two. So if you do with replacement, that is theoretically a better approach for sampling. So with replacement is better. Why? Because each selection probability is the same, remains the same over multiple samples. So what does that mean? So for example, so let's say you have extracted 35. Once you have extracted 35, 35 is placed back into the data set, meaning that your data set always remains of size 100. And then you extract 66. So the probability for extracting 66 is 1 over 100. The probability of extracting the first example, 35, was also 1 over 100. So second example is also 1 over 100. Even the 99th example will also be 1 over 100. So the probability for extracting remains essentially the same as you extract more examples from the data set. As such, the extraction is unbiased in this sense. While if you do it with replacement, So let's say you extracted 35 and then you extract 66. So 35 की जो probability extraction की होगी 1/100 है, 66 की 1/99 है, and if you go further, maybe at the end of the day, you might have 1/3 or 1/2, which is a very high probability. So the extraction probability increases as you extract more examples. So which in a way can give you a distorted view of the data set. Okay, I hope this distinction is clear. Now, the question is, which one should we use? So theoretically, yes, with replacement is with replacement is preferred. But sometimes implementation might be slightly tricky because you will have to, and of course, it might give you duplicates also. But let's say if your data set is huge, massive, let's say your data set number of observations n is, let's say, 100,000. And you want to take a sample of size, let's say, only, let's say 500, let's say. So in this case, the probabilities may not change significantly, even if you do without replacement. Okay? So essentially, when you are selecting the 500 example, the probability for selecting from the remaining would be 1 over, what would that be? 99,500. So it's not a big difference from the start, which was 1 over 100,000. Okay? So simple random sampling with replacement and without replacement. So without replacement is generally preferred unless duplicates are an issue. And so you can do without replacement, especially if your data set is very large. Because then even the theoretical issue of non-uniform selection probability is not an issue practically. You can do simple random sampling with some other groupings as well, so which we call the stratified slash clustered sampling. So the idea here is that you find stratas or you find clusters, as we saw before, you can do clustering. And then you do sampling within each strata or each cluster. And that sampling can also be done using SRS, simple random sampling with or without replacement. So why would we prefer stratified? This is generally preferred if you want to have representation from different strata or clusters of the data. So for example, if you think of the LUMS student population, so for example, the master student body at LUMS is much smaller as compared to the undergrad student body. So if you do simple random sampling, of course, you will get fewer master students as opposed to graduate students, undergrad students. But if you want to maintain some healthy number of master students, then you can cluster the data or strata the data. So graduate student is one strata and undergrad is the other strata. And then you do sampling separately in both of those stratas. In this way, you can control the number of samples from graduate students and the number of samples from undergrad students. All right. Any questions? Okay. So let's see. Okay, finally, I talked about three broad categories. So the last one was compression. So compression can also be done. Of course, compression is an algorithmic way of putting a large number of values into a smaller data size. Uh, but uh, so this is, of course, a way of reducing data, but there are not too many algorithms that will work effectively on compressed data. So you need to be aware of the limitations of the algorithms or the various libraries that you are using for data analysis, and then think about using compressed data for analysis. So for example, you can zip multiple documents, but for your algorithm to understand that zip and be able to process all those documents properly uh, is somewhat difficult unless it is, of course, specifically programmed to do so. So you need to be aware of these limitations. So compression, of course, can be used to reduce data size, but our goal, of course, is some analysis, some tasks that we want to apply. We need to make sure that that task is applicable or can be done on the compressed data. Okay. So in the book, there is a greater mention of compression. Even they talk about wavelet compression and stuff like that. But for most practical application or many practical applications, they are not very appropriate. Maybe for time series or spatial temporal data, they might be more appropriate. But most tabular data sets, compression wouldn't work very well. Okay, I think I missed one thing. So while numerosity reduction, there's another category of techniques which is called aggregation. So aggregation is basically trying to summarize your data in some logical way, and as a result, you are reducing the size of the data. So aggregation, of course, would be domain dependent, and mostly it's applied to data sets in which you have hierarchies of attribute values. Uh, so for example, let's say you have sales data from multiple stores, and for each store, there are, for example, multiple departments within those stores. So I can say, for example, so let's say if I write store A, and within store A, there is, for example, electronics, there is, let's say, clothing. And let's say I have sales count listed here. Let's say 25 here, and let's say 50 here. I'm just giving some numbers, small numbers. So this is for store A. Similarly, you will have for store B. So we have electronics and you have clothing. So let's say this is 50 and 25, or let's say change this number 50 and 50. Okay. So this was the detailed data set, but you can aggregate this data set. For example, you can aggregate all sales at a store. So for example, then store A, you'll just be left with one value, which is 75. And for store B, you are left with one value, which is 100. And if you want to do further aggregation, you can combine both stores and you will get 175. So there is a reduction going on here. So, so this kind of reduction is also possible through aggregation, and your data set will tell you if this is possible or not. So generally, you can think of this kind of reduction occurring in transactional data sets, uh, which have attributes with multiple hierarchies. And you can think in terms of data cubes. So data cubes are then aggregated along various dimensions. So you can aggregate them and collapse some dimensions. So I think I will probably stop here. You have a quiz at 1:35. And by the way, we have completed data reduction. And next we'll talk about normalization and we'll be done with this chapter. So any questions? Any questions? Any questions? So please get ready for the quiz. Put your cameras on and join Zoom as well as you need to log into LMS.
Alright, अस्सलाम वालेकुम everyone. Your quiz 2 is already up. और जैसे आप लोगों को पता है कि क्विज लीनियर फैशन में होगा, यू कैन नॉट गो बैक. दूसरा ये कि प्लीज मेक श्योर कि आप सब अपना कैमरा ऑन रखें, क्योंकि लास्ट टाइम देयर वर लॉट ऑफ स्टूडेंट्स जो कि प्रेजेंट नहीं थे जूम सेशन में. तो इस दफा अगर कोई प्रेजेंट नहीं होगा तो उसका क्विज काउंट नहीं होगा. अभी 135 नहीं हुए, जस्ट वेट टिल देन. अभी 133 में.